All right, can everyone online hear me?
Yes.
All right. Let me just make sure the cube is on. All right, can everyone online hear me? Yep. Oh, sorry, yes. I forgot to close the stream. All right. Let's make sure the cube is on. Okay, so we're going to get started with the Python simple linear regression homework. I'm going to assume that a lot of us are pretty familiar with linear regression by now. So I'm going to kind of focus a little bit on some other, aspects of the analysis that we're going to go through. All right, so we're going to work with this data set, FARS, whatever that means. So we're just going to go ahead and import it. Import our libraries first. Then import the data set. And one of the first things that you should do whenever you're working with a new data set is just kind of, take a look at it. Look at the columns, look at the values in the columns and try to make sense of what it means. So,
hey Matt, can you share your screen, please?
Oh, I'm sorry.
Thanks.
All right, so we have our data frame here. So what does one row in this data frame represent? I don't know about that, because if you look here, we have this case number 2. These 4 observations all share a case number, right? Within this case number, we have 3 vnums, which I'm guessing is vehicle number. And within each vehicle, it looks like we have pnum. So we're going to guess that's passenger number. And if available, you should always look at a data dictionary anytime you download a new data set. So that you don't have to kind of like infer this stuff yourself. But basically, the question I'm getting at is, does it make sense if each observation is a person, right? Like if each observation is an accident, how can an accident have a sex? Or how can an accident have a make and a model? Oh, well, yeah, okay. So maybe that's an outlier. We also have age, things like that. So it seems like each observation in this data set is a person that was involved in an accident. And it seems like a case is an accident. And again, if you ever get a data set from somebody you're working with, or in a professional setting, you should always sit down with the person who gave you the data and make sure you know what each column means, so that you're not just kind of guessing like we are here about like, what does body of 4 mean? What does sex of 9 mean? Maybe it actually means something and it's not just a typo or whatever. We don't know just from what we're looking at here. But yeah, just pointing out some EDA stuff. Another thing that you should always do when you're first looking at a data set is just do a quick check for the missingness. So does anyone have some code that they can share to just quickly check how many missings are in this data set and where? Yeah, so we can filter with a mask here using isNull.any. Okay, that was weird. And we're going to set axis equals 1 because we want to look for rows where we have nulls. Real quick, just going to. Just so we can see all the columns. So when we run this, we see we have 2 rows that have missing values. One has a missing value in this impact column, and one has a missing value in travel speed. So there's only 2 missing. So it looks like our data is quite clean. And now we can move on just after taking a quick look around. To number 1. So study the relationship of vehicle speeds and the accident counts. Use panda's cut function to bin the travel speed into 20 bins and introduce a new column of bin numbers. So can anyone, does anyone share code for the binning? All right, Charles, do you want to talk through your code?
Sure.
I do not know why this is not pasting.
You're on a Mac?
Yeah, I know. I'm doing command. Oh my God. Okay, there we go. All right.
All right, so I just said make a new column called speed bin. So after speed bin, you can do pd.cut. I'm going to cut the travel speed column into 20 equal sized bins. And I say new data from X is just equal to accident side. And I group by the speed bin. And I just want to look at the travel speed, and I want to aggregate onto the mean and count for each bin.
All right, so we're going to go ahead and run this. And you can see what our X looks like. So I think you were supposed to use the labels equals false argument right here. And what that's going to do is it's just going to have it label your bins by like simple numeric labeling instead of actually giving it the bounds as a label. And it's just going to make us like easier to work with. So we can just say bin 0 instead of bin 0 to 49 point whatever. All right, so this is our bin speeds. Now we're going to run a simple linear regression of 20 samples of accident counts against average speeds. Does anyone, or let me check, yeah. Does anyone want to share code for this? Okay, Charles again. Do you want to talk about this code a little bit?
Sure. So I made essentially a linear regression object, L equals linear regression. I fit the linear model using the independent variables mean, dependent variable count. And I just print out the intercept coefficient that the model calculated for us.
Yeah, perfect. So, yeah, I mean, the code is fairly simple. The only thing to remember here is you have to pass the features as a 2-dimensional object, even if it's, in this case, we're only using a single feature because this is simple linear regression. You still have to pass a data frame as the features, or else sklearn will not work. Like none of the model functions will work. So yeah, this is good. I don't think there are too many alternate answers here. So I'm just going to go along. We're going to plot it. Oh. Can you use Plotly? Call it mean. All right, I do not know what is going on with the computer today. I'm sorry, guys.
You just say X dot plot dot scatter. But if you map top of the line, you get the arrow.
Oh, good catch. I do not think I did that. It's like this, right? Okay, there we go. So what we can see from this scatter plot is it looks like our 95 to 100 mile per hour band or whatever it is has way more count of accidents, or in this case, people involved in accidents than any of the other speed bins. So we want to maybe remove this outlier to see if it cleans up our model at all. So does anyone want to share the code for removing this last bin here? Okay, so Charles filtered it for counts less than 5,000. So that's a fine way to do it. You could also filter it directly on the bin. So you could do something like that would also work. But yeah, this is fine. And we have our plot here, so you can see a lot more of the kind of granularity of the data when you don't have this one data point. Basically determining the scale all by itself. And then we are going to make a model. Yeah, what David posted would be fine as well. That's essentially the same thing as as this line of code here. So now we're going to fit the model without the outlier. So we're now using our Y data frame. It has the same features. So I'm just going to go ahead and run this. Oh. Oh, God. Yeah, so we print the intercept and the slope of the new model. And we can see that we no longer have a slope of like whatever it was in the first case, 100 with an intercept of negative 2,000 because we don't have this data point. Just as a quick aside, you probably, does anyone see a problem with removing this outlier? Could you pass him the cube? Jung, right?
Yeah. There's a whole lot of the outlier actually, right?
Right. Remember this. So our Y value here is the count of observations in each
Yeah.
bin, right?
Yeah.
So we're not actually throwing out one outlier here. We're actually throwing out a majority of the
40,000.
data set,
Yeah.
right? And this is also like where, where the most people are getting in accidents is in this speed range. So we actually in a real life situation probably would not want to handle it this way and throw out this data, but this is just to kind of illustrate the effect that one big outlier can have on a regression fit, and the improvement that you get after you remove that outlier.
Yep.
Another way to deal with this is using models that are less sensitive to outliers. One such being the Huber regressor. I mean, if anyone wants to post code for this, they can, but otherwise it's basically going to be the same thing that we just did.
Wait, man, I have a question.
Yeah, go ahead.
I mean, technically, by the definition of an outlier, wouldn't like all the points less than like the last like all the bins outside of the last bin, wouldn't they be considered outliers technically? Because there's so much of like the count of like the last bin is like it's like more than half of the total count. Like, you know what I'm trying to say? Like,
Well,
in a sense, like.
I mean, if we just look at
I don't know. This was just a.
there's not really a uniform way that you need to think about outliers. Like you shouldn't just go to your data set and say, okay, anything that's more than like 2 or 3 standard deviations is an outlier, and I'm going to throw it out before you even get started. You should run your models, see if there are any data points that are look deviant or cause bad results for the model or don't fit the model very well. And then you should see, okay, is there a reason why these points are, like if I go through and I look at the feature of these points, is there something that's making them behave badly? Is there something else I need to account for? Should I throw them out? You shouldn't just kind of take a blanket approach to removing outliers. So yeah, I think you have a point, which is that maybe since this is the majority of the data set, maybe all of these could actually be considered outliers. But I mean, that's kind of the point I was trying to make, is that when you group the data like this, you can't really just call this one point and call it an outlier, because it actually contains 40,000 rows in this bin. All right, so yeah, the Huber regressor, it's basically going to be the same thing. We're going to run it on the data set before the outlier removal. So we're going to run it on X. And we get our Huber regressor object. And you can see that the model generated by the Huber regression is much more similar to the model with the outlier gone. You can see we have an intercept of about 1,000 and a single-digit positive slope, versus our simple linear regression. We had a very drastic effect of the outlier versus the Huber regression. Even when we include the outlier, it behaves pretty similarly to the data set with the outlier removed. Now we're going to go into kind of the theory behind the Huber regressor a little bit. So here we can see this image of, have you guys talked about loss functions yet in lecture? Yeah? Yeah, so if the blue, so the blue is the RSS loss function, which is just the, the root sum of squares, the function that the simple linear regression is trying to minimize, basically. You have that here. And then in green, we have our Huber loss. And basically, Huber loss is quadratic at error less than this epsilon hyperparameter, and linear at error greater than epsilon. So what this means is that based on where you set your epsilon, anything with a deviation of larger than epsilon kind of gets its error mitigated. And so that kind of reduces the effects of the outliers, and you can set the value of epsilon to kind of adjust your outlier tolerance in the model. With this line right here. And if you ever need to, if you're ever wondering like how to set a certain parameter or see what the parameters are, I think you guys should probably know this by now, but just in case anyone hasn't, you can just press Shift Tab inside the function and then expand it, and it'll show you the whole documentation. So we can see that the default value for epsilon is 1.35. It's running 1,000 or 100 iterations to optimize the model. It's using this alpha, warm start, fit, intercept. And so you can change all of these things. You can set them to a default, and you'll learn methods to kind of find the optimal values for all of these parameters a little bit later in the course.
So now that we like the alpha, that's the alpha that we're gonna be
I think this model, I believe you can implement it with a penalization, but they start with an extremely small alpha because they want it to act, I think, like a simple linear regression by default. But you could also tune the epsilon the same way that you would for the alpha. And did you guys do like grid search yet?
Negative.
Yeah. That's,
Okay, yeah, so you could do something like grid search to find the epsilon to find the kind of outlier sensitivity that would give you the highest accuracy.
So when would you use?
Sorry, can you use the cube?
Sorry if this is a little repetitive, but when would you use just regular, like simple or multiple linear regression as opposed to the Huber model?
In my experience, in a real world scenario, you would almost never use simple linear regression over penalized.
Okay.
Because have you guys talked about like bias variance and like overfitting at all?
We got into it today. Yeah.
Yeah, so because a simple linear regression doesn't have the ability to, like it has no hyperparameters, it has no way to really judge how much it's overfitting or how much information it's taking from the data set. It tends to overfit pretty heavily. Whereas with penalized linear regression, you can adjust the alpha, you can adjust how much like coefficient space that it has to allocate to across all the different features, and you can use that to adjust kind of the how fitted the model is to the training data, and therefore how generalizable it is to test data.
Okay. Okay. Thank you.
So yeah, from this point on in the course, I think you will almost never be using simple linear models over penalized. Okay, so now on to question 2. To study the relationship between the number of injured people in an accident against the speed, do it in 2 ways. And this question, I think the question is a little bit incorrect. This should be the severity of injured people, not the number. But we'll just go with it. So we're going to run a simple linear regression on the total data set after removing the rows with missing values. And then we're going to do a linear regression on the speed binned data set. So first, using the full data set after removing the row, does anyone want to share their code for doing this? Okay, so we have a couple answers. So Oh. Do you want to? No, it's just because your computer's backticks aren't recognized as, or your quotes aren't recognized as quotes by this machine. All right, Jung, do you want to explain your answer?
Yeah. Yeah, so it's like the same thing as the first question. And so I'm fitting C, which is the
So you
travel.
found all rows and travel speed.
Yeah. And then,
Two NumPy. I don't think you don't need to do this.
hey man, I tried to do what worked. It worked and I got the answer, so it worked. That's
Oh. No, it's just more. It's more quotes.
Yeah, I told you, dog, it was working. Intercept 1.78. Lower 0.0092. Yes.
Yeah. So no, this works. So he's using the not NA method to filter out things from the travel speed column that are NA, and then he is using loc to only select travel speed. I think this will run if it even if you take these out.
Wait, yo, it wasn't working last time.
Oh, but okay. So this is probably
The ends justify the means. That's all I have to say.
yeah. So the problem with that you had while you had to do that is that it was thinking this C was a one-dimensional object and you only did this because it was a series. If you tell it that it's a data frame, then that should just work without doing all that. So you always got to remember that sklearn models always need a two-dimensional object as your input for your features. Which shouldn't be a problem like at any point beyond this because you'll always have multiple features if you're doing anything but simple linear regression. No, your target is generally going to be one-dimensional. The question was, do you need your Y to be two-dimensional as well? And then we also have code from David and Hadar. So yeah, this is great as well. Oh, so here's David's whole answer. Yeah, David, do you want to explain this? I think this should be basically the same thing as, yeah. So he basically did the same thing as Jung. He filtered out the nulls using this tilde operator, which means it's the logical not within a pandas filtering operation. So you can do not travel speed as null, and that will work as well. And then to get the model to recognize his travel speed series as a two-dimensional object, he reshaped it -1, 1 to get pandas to interpret it as a data frame with one column instead of a series. So yeah, this is also good. And then Hadar, yeah, so she removed the nulls by using this drop NA method, and that is fine as well. So now moving on to the second part of the question. We are going to fit a model on the group data set. Does anyone want to share code for this? Do you want to explain what you did, David? I guess not. Oh, okay. So he's grouping by the speed bin, taking the injury and travel speed columns from the grouped data frame, which I don't think you need to do. This should work without this. Yeah. Because the ag function in pandas is very similar to the summarize in R, where it only keeps the like aggregated features that you create, that you define in the ag function, and ignores everything else. So it doesn't matter if you kept other columns in here, because it'll just get rid of them all anyway, and it'll only output a data frame with the aggregated features that you define in your functions here. He then renamed the columns and then made his scatter plot. So yeah, this is good. Sherry, is that right, Sherry? Sherry? Okay, so yeah, this looks like basically exactly the same thing. A quick note on the ag function is you can also do a dictionary where each element of the dictionary is what you want to do to that feature from the original data set. So this is another common way to do aggregation, is to use this dictionary notation like this. This should do the exact same thing as what David has done here. The only disadvantage with this is that you can't actually set the new column names that it outputs, whereas here you can. So you also don't need, or you also didn't need to do this renaming operation here, because you already set the names of your new output columns in your aggregation function. But renaming it doesn't do anything, so it's fine. All right, so now I'm just going to do this part because I think everyone should have an idea of how this works by now. So this is Z. And we are looking at injury versus travel speed versus injury. Oh yeah, go ahead.
It's not the last.
Can you pass her the cube?
Just for the chunk above, like, is there a way to simplify the code to the same format that we use that was in Charles's answer from like the first time we used ag, where you can just say mean and count? Or is it that because we have both trav speed and injury, like you can't just say,
Let me.
you have to specify in the ag, like
Was it here?
the injury under fit in OLS on the group by data set? Oh, wait. Oh yeah, exactly. Like
So
just exactly like that. Like, or is that
this
we can't do that because
won't
we're doing both?
work
trav speed.
because we're taking multiple features and we're running aggregating functions over them. In this one, he's only taking one column
Right. So you don't have to
from the
specify.
entire data set, and then he doesn't have to specify which features he wants to aggregate because he only has one feature.
Yeah, sorry. That, I guess that's kind of obvious. My bad.
Okay, so we see that we get a very different intercept and slope when we bin it by the travel speed versus when we don't. even though it looks like we do have a pretty nice linear, trend between how fast you're going and how bad you get injured. So why might this not be entirely correct, this model here? Right. But why is that a problem? Yeah, John?
So it's not taking consideration of the weight of each bin.
Yeah, remember how we were talking about earlier, how this bin that we threw out as an outlier earlier actually has like 60% of the data set in it?
Yeah.
This model treats each of these bins as an equal data point. So it's not taking into account the fact that there's way more people in this bin than any of these other bins.
Yes, sir.
So in order to get around this, we're going to do a weighted linear regression. And I'm just gonna do this again because it should be pretty simple. So we're just going to pass a third argument to the model, and that'll tell us how to weight each bin. In this case, we're telling it to weight by the count. So we run this, and now we see that we basically have an identical model to when we did not group the data set. We have Intercept 1.7. Okay, so it's almost identical, but yeah, so you see when we correctly weight these bins, we get the same model. Now, are the residuals normally distributed? So let's study the residuals of the simple linear model on the entire data set without grouping and display a histogram of it. So who can give me code to get our residuals here?
Hey, sorry, I have a question about like for the part where we do the ag function.
Mhm.
I keep getting a warning message that indexing with multiple keys is going to be deprecated, and so we should use a list. And I was wondering, yeah, why
Did you put
happening.
the features in here?
I did. Oh, is that why?
I think that's why you get it.
Oh, okay. Oh, yeah. Okay.
Yeah, so I think I would stay away from doing this because again, the ag function is defining what you're taking from the what features that you're taking, and you're going to output in the aggregated data frame. So you don't need to like define what columns you're taking
That
in
makes
here.
sense. Yeah, that's just redundant. Okay.
All right, so going back down here. So yeah, residuals, it's pretty simple with sklearn. You just take the actual values and then you subtract the predicted values. Let me just make sure your model's name is the same as what we have here. Yeah, LM2. Did you use as plot? Yeah. So what we're seeing here is that we should not use this model. What do these residuals look like to everybody? Yeah, not normal. So yeah, this violates one of the assumptions of linear regression, which is that the residuals are normally distributed. And then we do the same thing here on the injury itself. And so we can see that you know, the actual injury data is also not normally distributed, and this isn't necessarily a problem. So remember that it only matters for linear regression whether the residuals are normal. But a lot of times when you don't have normal data, that's when you don't have normal residuals, right? Because if the travel speed is following kind of a smooth curve, and there is the injury, the other variable that we're plotting it against is very, non-normally distributed, then the residuals are going to be non-normal. So yeah, this is probably a bad model.
Do you think that has to do with like the way we're interpreting injury as like a count instead of as like a
Well, we're not interpreting it as a
Category.
count because we have one injury for every person, right?
oh okay.
Yeah, I mean, I was saying that the number of injured people here is probably not exactly correct.
Oh, I thought you were saying
So my guess is it's injury severity, but it could also be like codes for like 4 is like whiplash, 3 is like, so it might not even be a progression. Like 1 might just mean a specific type of injury, 2 might mean a different specific type of injury. And again, this is why you should always try to get a data dictionary for a new data set that you're looking at. So you're not just kind of like guessing like this, because it's entirely possible that like 4 is actually,
whiplash.
like,
yeah.
like maybe one of them is like you died or like, I don't know. So
And in that case, like you wouldn't expect to see any sort of normal distribution because it's just
yeah,
categorical.
this could just be, categorical variables that aren't necessarily in any kind of like order. Whereas, when we do this analysis, we're kind of assuming that they are without knowing. So now we're going to look at the relationship between the number of samples and the standard errors. So we're going to use stats models for this. So I'll go ahead and import stats models. Date tools. Okay, we might have some kind of library conflict on the streaming computer, which is not good. If I just take the OLS function. So we're missing this object in pandas. Okay, I might switch over to my personal computer because I do not think I have time to sort this out right now. Sorry about this, everyone. Where are we? So we are down here. Can everyone still hear me?
Yeah, you're good.
Okay. All right. So we import stats models. Remember with stats models, you're going to need to do this add constant so that you create a feature. Oh, Okay, sorry about that, everyone. Yeah, so we are going to take our travel speed from accidents 2. We're going to add a constant to it using this add constant function from stats models. That's going to give it just an entire column of 1s so that we can fit our intercept to this. You don't need to do this with sklearn, and it'll do intercepts for you automatically. But if you're using the linear regression functions from stats models, you need to remember to add a constant if you want to fit an intercept. I think just because it gives you this kind of nice output that sklearn doesn't about your model, and it wants you to get these, the intercept, slope, and standard error of the coefficients in your model. So, this is an easy way to do that, but I would stick to using sklearn. Like the way sklearn is set up is kind of more bare bones. Like it doesn't give you nice outputs or anything, and it just really focuses on like algorithmic speed and simplicity, which kind of matters a lot more when you're doing more complex models. Yeah, I do not have too much time left, so I'm just kind of going to go through this. So we fit our model, we get our summary using the .summary method, and we can see here that we have our coefficient for our intercept is this, and our travel speed is this, so it matches the models that we made with sklearn. And it gives us our standard errors for each of our coefficients here. It says we have 0 standard error for our travel speed. So we're going to go and look at this in a little bit more detail because I'm guessing that the chart here just doesn't have enough decimals. Yeah, so we can see here are coefficients using the parameters method of the model after you fit it. And then the BSE, I'm not exactly sure what the B stands for, but I'm guessing the SE is standard error. So that'll output your coefficients and your standard errors. Now, going to the second part of the question, use Numpy random choice to randomly select 100 samples and rerun the linear model. What happens to the intercept, slope, and standard errors? So to explain this code a little bit, we import Numpy here. We're going to generate random, basically batches of 100 random indices from our data set without replacement so that we can't be taking the same person twice. From there, we're going to filter our data frame for the random indexes that we just generated. We're going to add a constant so we can fit the intercept, and then train a model on just these 100 samples out of our data set. So you can see here that the coefficients are, pretty comparable. We went from 1.78 to 1.61 and 0.009 to 0.01, but our standard errors are much higher. And this is generally what, the effect of changing the sample size will be. We had 65,000 data points for this model, and we only had 100 for this one. So you're going to expect that our errors are going to be a lot bigger. To print that out in more detail, we have this. And lastly, to estimate our standard errors through resampling, this is going to be similar to the bootstrapping that we talked about in R. So we're going to initialize these empty lists to hold the coefficients and intercepts from each iteration of our bootstrapping. We're going to run 1,000 iterations. Again, we're going to generate 100 random indices. for each iteration, we're going to create a sample of those 100 indices. We're going to train a model on that sample. And then we're going to store the parameters of that model into our lists here. So when we run this, it's going to take a second because we're training 1,000 models. All right, and lastly, we're going to visually inspect our intercepts and our slopes. So you can see that the distribution of all of our samples of intercepts are kind of centered around the true mean, I guess, that the sample using the entire data set found of 1.78-ish. And our slopes are centered around the, that 0.01 approximate. And then if we take the mean of the coefficients and intercepts, we see that we're very close to that, 0.01, 0.009, whatever it was, and the 1.78. And again, why do we bootstrap? Does anyone remember from last time when we talked about it in R? So bootstrapping, basically, I wouldn't argue that you would need to do it for this data set because we already have 65,000 data points. When you would want to do bootstrapping is when you have a small data set, and basically the assumption is if you're confident that your sample was taken well, so like if your sample, all the observations are independent, and if it was truly randomly drawn from the overall population, then your sample should be a representative sample of the population, right? And if your sample is representative, then resampling from the sample should be statistically equivalent to taking more samples from the overall population. I can kind of write that down somewhere once. Oh, sorry. And so basically, what this means is that we saw, our sample for our model, when we only ran it on a sample of 100, had much wider, where is it? Here, had much wider confidence intervals and much larger standard errors, right? So if I have a small sample, but I'm confident it's a good sample, then I can bootstrap to get a kind of, artificially higher sample size and reduce my standard errors. And then lastly, here are the standard errors of the groups of intercepts and coefficients. Does anyone have any questions about this homework? Sorry for the technical issues. All right. So that is it for simple linear regression, and you guys just have project time now? Okay. So I'll leave the room open. I'll make breakout rooms, and Yeah, thank you. In case online people want to go in breakout rooms to work on the project.